Artemis II will face a short window during re-entry where communication with Earth is completely lost. For about 4 minutes, no one on the ground will be able to see or hear what's happening inside the spacecraft. When Orion enters the atmosphere at around 40,000 kilometers per hour, the air around it ionizes into plasma. That plasma blocks radio signals. Inside the capsule, the crew will see the windows glow and feel the G-forces increase as the vehicle slows down. In Houston, Mission Control will temporarily lose all data. This is expected. Once the plasma clears, communication returns, assuming everything is working as it should. The crew, Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen, launched from Kennedy Space Center on April 1, 2026. This is the first time humans have traveled beyond low Earth orbit since Apollo 17 in 1972. Their path takes them tens of thousands of kilometers from Earth and around the far side of the Moon, farther than any crew has gone before. But the most critical part of the mission isn't getting there, it's coming back. Re-entry is where everything has to work. The mission lasts about 10 days, but the most important phase is the final few minutes. During peak heating, the exterior of the capsule reaches temperatures above 2,700 degrees Celsius. At the same time, communication drops out and the heat shield has to perform exactly as designed. There's no way to intervene during that window. The system either works or it doesn't. For comparison, spacecraft returning from the International Space Station re-enter at about 28,000 kilometers per hour. Orion is coming in significantly faster, over 40,000 kilometers per hour. At those speeds, the air can't move out of the way fast enough. It compresses, heats up, and turns into plasma. Without protection, the structure of the spacecraft wouldn't last. That protection comes from a material called Avcoat. It's an ablative heat shield, which means it absorbs heat by slowly burning away. As the outer layer chars and erodes, it carries heat with it, protecting the structure underneath. This approach was used successfully during the Apollo missions. For Orion, the manufacturing process was updated. Instead of a single honeycomb filled with material, the heat shield is built from pre-formed blocks bonded together. It simplified production, but it also introduced some uncertainty about how the material would behave under real conditions. That question was partially answered during Artemis I in 2022. The mission itself went well, but when engineers inspected the heat shield afterward, they found more damage than expected. Some areas showed irregular cracking and material loss that didn't match predictions. This was linked to the type of re-entry used. Artemis I used what's called a skip re-entry. The capsule briefly dipped into the atmosphere, then climbed back out before making a final descent. It helps with landing precision, but it also changes how heat builds up and dissipates. During that process, gases inside the heat shield material became trapped and later released unevenly, causing parts of the surface to break away. Even with that damage, the internal temperature of the capsule stayed within safe limits. The system worked, but not in a fully predictable way. For Artemis II, NASA decided not to replace the heat shield. Instead, they adjusted the re-entry profile. The skip maneuver has been removed. Orion will now follow a more direct path through the atmosphere. That increases peak forces and heating slightly, but it avoids the conditions that caused the earlier material issues. Testing suggests the updated approach keeps the spacecraft within safe limits, even if some material loss occurs. Still, re-entry remains one of the highest risk phases of the mission. During those 4 minutes of communication blackout, Mission Control won't be able to monitor anything in real time. This has been a known limitation since the earliest days of human spaceflight. At hypersonic speeds, plasma simply blocks radio signals. The crew will rely entirely on the spacecraft's systems until communication returns. There's historical context for this. During Apollo 13, re-entry communication lasted longer than expected, creating uncertainty until contact was restored. In contrast, the Columbia accident in 2003 showed what can happen when thermal protection fails. Re-entry isn't just routine, it's where margins are tight and timing matters. The angle of entry has to be precise. Too shallow and the spacecraft can skip off the atmosphere. Too steep and the heat and forces increase beyond safe limits. Orion's heat shield is about 5 meters wide, made up of Avcoat blocks a few centimeters thick. That thin layer is what protects the crew from extreme temperatures during descent. After the heating phase, parachutes deploy in sequence to slow the capsule for splashdown in the Pacific Ocean. If everything works as planned, Artemis II will confirm that Orion can safely carry astronauts to deep space and back. That's a requirement before future missions, including a lunar landing, can move forward. There are additional risks as well, including radiation exposure beyond Earth's protective magnetic field. Orion includes a small shielded area for solar events, but it hasn't been tested in a worst-case scenario with a crew on board. The astronauts are aware of all of this. They've reviewed the data, the risks, and the previous mission results, and they've chosen to fly. As Orion approaches Earth, the service module separates and burns up in the atmosphere. The crew module continues alone, orienting its heat shield forward. Within minutes, temperatures rise, plasma forms, and communication cuts out. For 4 minutes, everything depends on the spacecraft. When the signal returns, mission control will know the outcome immediately. Artemis II isn't just about reaching the moon, it's about proving the crew can come back safely. We'll know the result soon.